This is my 4-bit microprocessor. Each location within the prompt code has one specific instruction and is executed sequentially because of the counter and the clock. Half of those output bits make up the opcode, here it is a 1, for the instruction decoder, which then determines what the rest of the processor does through the control bits. The other half of the data goes as data values into the data mux, which selects either the data from the PROM or the data from the ALU accumulator to be forwarded into the register file. The ALU receives the data from the register file and can then make use of all the different functions. It has an accumulator, which is a register that stores the output data from addition or subtraction, or and XOR operations, whenever the write enable is high. Here's my 4-bit register subcircuit and my 1-bit register. To also be able to do hardware subtraction, I added this input pin and modified the 4-bit full adder to also have XOR gates. If the control bit is enabled with a 1, the XOR gates create the invert of the B inputs. Together with the 1, which serve as the add 1 on the carry-in, we can create the 2's complement and therefore do the hardware version of subtraction. On low, it does addition as usual. The subcircuits of the OR, AND, or XOR, OR, AND, or XOR. The register file consists of 2 registers. In one of the 2 registers at a time, the data received from the mux can be stored depending on the control inputs. The register subcircuits are the same as the ALU register, but here's the write decoder. Finally, the output of the register file goes as ASCII code into the ASCII display, so we can read the code. Every instruction is executed sequentially. As you can see when I turn on the clock, it starts with hello, Brother Davies, BB. Then we have some addition, where each hex code is first stored individually in the registers and then sent to the display. And the same goes then for the addition, because we first have to display them, and then for the actual addition we are using the adder function and then store them within the accumulator, which then gets sent over here to the mux and into the register file. And then with the multiplication we do the same thing, because 3 times 3 is the same as 3 plus 3 plus 3, except we actually store some in there. To make that then is 6, and then we add 3 again, and then it'll be a 9, which I can output right here. So now the next one is actually part of the software subtract, where I first convert a +3 with the XOR from in here, and then we also the add function, the add operation, to make it a 2's complement, and then I add the now -3 to a 4 and receive a 1, which is then being converted into ASCII code again to be displayed right here. And then the second version is the hardware subtraction, which I've already mentioned earlier within the subcircuit.